So, thank you for having me. I'm so happy to be here. So there is a long story about this talk. Like the metadata about this talk is that I quit my job at Microsoft a couple of weeks ago. So I am now traveling, and so I heard from many of my friends that Vietnam is awesome. Vietnam is a great place to go. So I said, okay, I want to go to Vietnam for 1 month. And so, of course, because that's what I do, I search for conferences that are happening between July and August, and I found this one. And I found my good friend Leon and Maurizio speaking here. So I say, oh, well, I'm going to attend. But unfortunately, I was late in buying the ticket, so I was lucky that one of the speakers dropped out. So I proposed myself as a speaker. So I'm here because I'm going to be in Vietnam for 1 month. This is my... next week I'm gonna rent a motorbike and I'm gonna drive all the way to Ho Chi Minh City. So I think I'm gonna see your beautiful country. All of it, almost all of it. But maybe I'll come back. So I'm Alessandro, this is my family. I call it a sovereign family. So all these kids over there, 2 are half Belgian. I'm from Italy, from south of Italy, and I moved to the Netherlands, north of Europe. 2 of the kids there are half Belgian, half Italian. The other 3 are half Dutch, half Greek. That's my Greek wife. So we are really European family. I don't know if you do also this, like, I don't know, a Vietnamese, marry a Korean, and then moves to Japan, right? So this is what we are. The conversation in Europe is all about sovereignty. We need to rebuild or build the capacity to take care of our own business, our own defense, our own AI, our own data centers, and so on. So that's why I decided to quit Microsoft, because I want to double down on the sovereign story in Europe. In Europe, and maybe help Vietnam also what we learn over there, and bring it over here, or learn from you, because you seem very advanced in sovereign everything. So, and I also rebooting this project called Kubespaces. So if you want to check it out, it's a multi-tenant virtual cluster manager for Kubernetes. I have some stickers over here, also stickers of the tag environmental sustainability. It doesn't exist anymore, but it's being rebooted. And I brought some t-shirts. So for you, I thought it was, I was thinking about a gift, and this is what I have. So these are, they are clean. They are t-shirts from Kubernetes, and this is from KubeCon Paris. So if you want, they are limited edition, so you should grab them while they are there. So, and I'm going to talk about today about a topic that really interests me, right? So I was, at some point, the tech lead for the Technical Advisory Group Environmental Sustainability of CNCF, which doesn't exist anymore, but it's being rebooted into a new group also about sustainability. Because sustainability is the most important conversation we should have, right? So if there is no planet, there is no future. If we consume all the resources we have, we need to think about how to make it better, right? So this is a topic that really matters to me. I have a big family, so I want them, my kids, to have a future. So all boils down to energy. Oh, by the way, I studied chemistry in a previous life, so I'm not a physicist, but chemistry is quite close to that. So what is a watt? Watt is a measure of energy or work or heat. It's the same thing, of course. It's the equivalence of energy, and heat equals energy. So the joule is the measure of the work that the system can do. And it's usually measured in joule, is the measure. And watt is the energy per second, is the flux of energy that flows through a system at any given time. So when you say, my air dryer is 700 watts, or this GPU is consuming 700 watts, means that 700 joules are flowing through the system per second. And so it's a measure of the rate of work, the rate of energy that flows through the system. And then we also use kilowatt hours to go back to actually the total amount of work. A kilowatt hour is 1,000 watts per 1 hour, right? So you divide again, or you multiply per time unit, so you go back to joules. So kilowatt hour is a measure of the total work that's been performed by the system. So it's a static measure of joule, while watt is the amount of the flow. You can see that a human brain is 20 watts. Seems little, so, and we haven't beat that yet, right? So we can't beat millions of years of evolution just in a few decades. So human brains is still the most efficient, the one that makes most work with the least amount of energy. And of course, NVIDIA, a GPU several kilowatt. And we are talking now about building gigafactories, gigawatt level AI data centers. That's the next frontier, right? So the Star Cloud thing is 500 gigawatt data centers project, this Star thing in US. For comparison, you know that 174,000 terawatt of energy hits the Earth at every second coming from the sun. So we are harnessing just a little bit of that. We're talking about only a fraction of what the Earth can provide us. And what is intelligence? Right, so how to measure intelligence? Also a physical problem. It's been calculated, of course. This is the amount of energy that it takes to delete 1 bit. It's the Boltzmann constants times the temperature times the logarithm of 2. So it's about, like, it's a very tiny amount of energy, but imagine how many bits we are talking about. Imagine how many bits are stored in your brain, right? So computation is a physical process. It takes energy to compute. It takes energy to think. And that's why we have to eat, so we can use that and convert that energy into thoughts. So this energy is an engineering problem. So we need to optimize energy consumption and energy flow through a system. So, and this is what we think is the Kremerian model. So it's very important for me because it strikes me as coherent, right? So as the population grows, right, so we are seeing an explosion of population. It means more brains, more human computational power, and all the major discoveries, they are just because there are more people thinking about it. We are building the same with AI. We're building more GPUs, more efficient algorithms. So obviously, we are unlocking more and more progress because of AI. So this is a power law of just amount of computation. And just by growing the human population, we almost defeat every disease in the world. We are about to crack fusion, sorry. So this is why intelligence is so important for us. It will unlock a better future, a brighter future for everybody. And if you are into sci-fi, this is the Kardashev scale. So we are going to, as a species, as a civilization, who knows the Kardashev scale? Amazing. So I'm a sci-fi fan. So as we harness more and more energy, we'll see that the limiting factor is how much energy we have. Like how much energy can we extract from our surrounding. We live on this planet. We are not a spacefaring civilization yet. So we need to harness all the power that we can on this planet, and then eventually maybe build a Dyson sphere around the sun, and then harness our star, and then eventually move to a galactic civilization. But if you don't know what it is, please look it up. It's a very fascinating idea. Imagine how much AI can we build if we can get all the power from the sun into data centers. So, too much? So, I read this, actually came out yesterday from Fortune. Agents are taking over the internet. I've seen the internet birth. I'm 50, so I remember a time before the internet and then a time after the internet. I remember that everybody was jumping on these forums and chatting to everybody, and it was so incredible to have a conversation with somebody in Vietnam while I was in Italy, right? So this was the big breakthrough of last century. And now we are moving towards a dead internet theory. He's the founder of Reddit. He says, well, large part of the internet are just dead. There is no human. They are just agents making Stripe purchases. Most of the internet now is more than 53% of the 50%, according to Cloudflare, 53% of the web requests are done by agents now. So more than half of the internet is powered and is meant for agents, not humans anymore. So we are out of the picture. So this is a very, I don't know, it's a different world, right? So we are giving out these tools to agents, and they are taking over. So more than 8,000% growth in traffic from agents. All these agents run on tokens, right? So that's where the smart comes from, right? So tokens is this is what I want to refute. My theory is token the new oil? No, it's not. Tokens is the gasoline, right? So tokens is what goes in the intelligence, and the watts, the energy, is the real measure, what we really have to care about, right? So tokens are kind of easy to make, right? So you buy some GPUs, you power the GPU, give a model, get some tokens, right? So your scheduler, your GPUs are the factory, right? So it's what stays in between pure energy, raw crude oil, and paracetamol, and gasoline, and everything, plastic, right? So the world runs on oil. The physical world runs on oil, but not just any oil. You extract crude from the ground, you refine it, and then you use it. Same with intelligence. You harvest energy, possibly good energy, renewable energy, not just burning oil, or it's also, burning oil is also energy, but it's energy that can be used for better things, like making pharmaceutical or other important things that we need in as a species. So as soon as you get this energy out of mostly the ground, most of the energy on Earth is stored in the ground. Some energy is stored, of course, in the sun. So wind, solar power is all due to the sun hitting the Earth with energy. But most of it, so once you get it, you need to refine it, and that's very important. That's where we are here, right? So we are engineers working on building this factory. So this is what the talk is about, how to make this refinery better so you get more tokens out of the same amount of energy. So it's not about the tokens anymore. So tokens are a commodity, right? So you get some open source model, closed source model, doesn't matter. What matters is how you convert energy into tokens, right? So Satya Nadella, my former CEO, I guess, said rightly so that the cost of tokens is halving every 3 months. It's pretty much like the Moore law, but even faster, I think, right? So that was every 2 years, right, or every year. Every 3 months, the cost of the tokens is going down. So the economics, the token economics is changing a lot, and it's kind of hard to understand, right? So how can I make money if my commodity gets cheaper? That's very important to understand, right? How can I sell and make more profit if my token price goes down? I need to work on my efficiency, like produce more tokens for less price. That's what unlocks. So tokens are a bit like, there is a name for it, I don't remember, but when a commodity gets cheaper, it's used even more. So eventually you're gonna use even more of that. So eventually you need to produce even more of those tokens, more of that commodity. So this is important. So as token gets cheaper, more people are gonna use it, more use cases are gonna be found out, and so we need to produce even more tokens. And if we use token as the same ratio of watt per token that we do today, we're gonna kill the planet. That's the bottom line. Right? So if we don't improve efficiency in token production, we're just never gonna be able to produce what we need. And again, like I was talking before, like there's these two worlds, right? So the data center world thinks in watts and you know, how much rack and how much cooling power, BTUs. You know, BTUs. I know what it is now, but you know, these are the language of the data center people. And then we work on the other side. That is kind of a black box for us. We work in Kubernetes, we work in OpenStack. So for us, it's all about, okay, how much GPU utilization I'm doing, you know? But we need to connect the two worlds and understand that they're all connected. They're all part of the same system. It's not two systems that completely separated, but there's one system that has to work together. So if we want to improve efficiency of the old system. So PUE is the power usage efficiency. 1.57 US average. You can go lower if you're an hyperscaler and you build very large data centers. You can go lower than that. But if you're a small data center operator, it's hard to get lower than that. So we probably squeeze as much as we can. We cannot get to 1, of course. 1 means every watt in the data center gets converted to usable energy for the computation. We're never going to get to 1, of course, but we can get closer. But there is a limit, right? We cannot just, there is dissipation over thermal dissipation and some of the other waste that you do in the data center. So we can work on getting better compute efficiency, getting better schedulers, better use what we have, the power that comes from the data center, in a better way in our compute. And first of all, of course, is that we need to see what's going on, right? So observability and scheduling, they go hand in hand. How can I place a workload if I don't know what the workload consumes? I don't know what my infrastructure looks like. And we go, in the very beginning, Kubernetes had just one scheduler, right? So very, very bare, nothing extensible. So in the infinite wisdom of who designed Kubernetes, so they made it extensible, so thankfully. But it was only really just CPU and memory. So nothing about how many GPUs I have, not about how much power I'm consuming. So we go from the first iteration of scheduler to all the way to a more comprehensive way of understanding what's going on. And then we came out with better schedulers that can look at different metrics and not just CPU and memory. So for example, we can see what the power consumption and the carbon emission, right? So this is very important. Like I'm going to show you, there's a way to understand what my carbon emission look like, what is how much carbon per unit of computation I'm emitting. Carbon means CO2, which is carbon equivalent. It's kind of a way of understanding your environmental impact. How many tons or grams of CO2 you are emitting per computation. I don't know if you noticed, there are some projects already that can add, you know, when you chat with ChatGPT or some other LLMs, you want to know not only the performance metrics, token per seconds, time to first token, all very important metrics, but also you want to know that query, that computation, how much CO2 emitted, and conversely, how many watts did I consume by asking LLM that question. And most important, you want to have perfect utilization, like increase the utilization of GPUs. So this the AMI talk this morning. This is the evil of computing, right? So buying something, reckoning in a data center, and leave it there, not utilized, but on. That's really, really bad. So it's on, potentially can make work, but it doesn't do it because we don't feed the GPU with enough computation, with enough work. There was a study from vast data, I think, but also it's not just a GPU problem, right? So most of the Kubernetes clusters out there are utilized 10 to 15%. This is a problem of cost, of impact, burden of operations. Like you have hundreds of clusters, each utilized to 10%. By the way, this is also why I came up with Kubespaces, but it's another topic. But we focus on GPUs and we want to utilize them as much as possible because we pay for them, right? So we want to make sure that they are doing what they are meant to do. Another way to measure, of course, you go to the source and you measure the power consumption of the GPU. And so this CNCF project, so it's a CNCF project, was under the Technical Advisory Group for Environmental Sustainability, called Kepler, is meant to capture the metrics directly from the Linux kernel, right? So the kernel knows everything about everything running, right? So it exposes counters and metrics and gauges and everything to understand for every process what is the power consumption. It's a great project to use a lot. Who use Kepler in your data center? Not yet. because it takes some effort to deploy, of course. It's an extra tool. It exposes Prometheus-style metrics that you can collect and then put it on a dashboard and see exactly, correlate your power consumption with what we're actually producing, for example, web requests or tokens, right? So this is important so you understand how that work translates to power consumption. And it can get data straight out of the NVIDIA DGGM, all sorts of things. It was recently, rewritten. So it was based on eBPF. Who knows what eBPF is? If you heard of Cilium, so eBPF is a very old mechanism in the kernel that exposes, that use microprograms that runs in the kernel. So it used that to extract. It used to use that to extract data out of the kernel, and it worked pretty well. Unfortunately, eBPF is a bit complicated, right? So it requires sudo access and these capabilities. So it was recently rewritten. There was a recent blog post on the CNCF blog where they now get the data out of proc and sys, right? So read-only, so everybody can read what's going on in /proc and /sys, so even Kepler now can get data, and it's more accurate, it's more close to the reality of what's going on, and it doesn't need elevated privileges or no more root to install it, and it's more close to the real consumption. So the blog post really says a lot. I want to show you just a couple of things. So this is what looks like. So imagine if you can attribute every workload to the right source, right? So you can attribute how many watts every part of your GPU cloud consumes. So, and then you can see that, so you can divide by inference and training, and maybe you can scale one after the other properly. And this is what you don't want to see, where you have utilization 0%, but still have idle power 95 watts. So this, if you don't use a GPU, this is what looks like. And if you see utilization going up, and you see also, of course, consumption going up, but that's healthy. And you want to stay in the 60–70% utilization because that leaves headroom. And you can use AMI, you can use other schedulers to have the best utilization for GPU. AMI, in particular, I just find out like a couple of days ago, is a great tool to squeeze more workloads into the same GPU and don't leave idle, unused resources on the table. Because you're still burning, but... So, if you are interested in Kepler, look into it. Okay. And if you have GPUs available, you can actually help the project by measuring the GPU consumption on load, when it's loading. And there is a machine learning model that helps predicting the power consumption. The problem is, with Kepler is that, of course, if you have bare metal, you can get these numbers very reliably. But if you're running on virtual machines, the proc and sys numbers don't mean much because the virtual machine doesn't have visibility into the underlying hypervisor. So they need to train a small machine learning model that predicts the consumption based on experience, based on data, and you can provide some of this if you have this available. And as I didn't know about AMI, so I didn't include it, but what I know is Kueue and KEDA. So this is important, so you can move temporarily, so not geographically. If you can, all the better. So you can, if you could move a workload from a place that has a very high price of kilowatt to a place where the price of kilowatt is lower, you will save money and possibly also save CO2 emitted. But imagine, or you can move it in time. Like if you have inference during the day, maybe there's a lot of users want inference, so you should allocate more GPU power to inference. And at night, maybe there is not much inference going on because people are sleeping, they are not asking any question, although with agents, of course, they don't sleep. And then you can reallocate part of that capacity to training. And you do this by using Kueue. Kueue is also a CNCF project. So you can schedule, this is purely a scheduler thing. It doesn't really know about GPUs. It's just something, it knows about what you tell Kueue to understand. So you can actually label a node, and you can add capacity power, acme.io, and you say 100,000, right? So, and you say that with this annotation, then the node will have this new label, power acme. It's totally arbitrary. You can choose one. But now Kueue will be able to use it to make an intelligent scheduling decision, not just based on the number of GPUs, but also now on the number of watt that node is consuming. And then you can say this node has 100 watts available, and I want to use 10,000, and then the scheduler will be able to help you out over there. So, I think almost done. So you can save by moving workloads across time. And then, I'm gonna skip this. If you don't do this, it's fine. Things are gonna run. It's not the end of the world, but you're gonna waste money, waste resources, keep very expensive equipment idle. So you're not really serving the planet or your employer because you are wasting time, you're wasting money and wasting power that can be used for something more useful on the table. So Kepler needs some tester, of course, if you have GPUs around. We rebooted the technical community group now, it's called TCG, Environmental Sustainability. We meet every now and then, every couple of weeks, occgroups.dev, and then search for environmental sustainability. It's a great place to discuss and to show that you care about these topics. Also there. So tomorrow you can deploy Kepler. Monday, the day after tomorrow, you can deploy Kepler, you can join the group, you can reclaim GPU capacity and maybe use AMI or other tools to be more conscious of what you do. And that's about it. This is me, AI refined, because yesterday the mausoleum was completely empty, so I just took a picture, but then I had to add more people in there. So thank you very much, and well, I hope you enjoyed. If you have any question. Yeah.
Thank you, Alessandro. And chúng ta sẽ có một vài phút, có vài câu hỏi nhé. Thì thời gian hết rồi thì
So thank you, sorry for the pronunciation. So that was really inspiring. So I have like 3 small questions. So you mentioned about KEDA. So what should be the event of the KEDA for like auto-scaling the workload in order to consume the energy more efficiently? And second is, what could be the matrix? What could be the good matrix for the watt consuming, I assume. And also for the KEDA, if you know about, is there any built-in scaler or external scaler for auto-scaling the workload based on the watt consumption? Thank you.
Good question, thank you. So when I was working in the environmental sustainability, of course, the trigger was the carbon intensity, which is, you know, how much CO2 is emitted per unit of work. And those triggers can come from public data. There is a thing called electricity maps. It works also in Vietnam, it works in Europe. You can actually see real time what's the mix of energy production from every country. So you can actually tie KEDA into that data. So when a country starts to become more red, you know, more polluting, you can move or you can scale down the workloads, because now you don't want to emit. You can also use carbon quota. Let's say I want to run my workload in this country. I'm fine until that amount of CO2. After that, I want to, you know, I don't want to pollute more than necessary. So when the carbon intensity becomes too big, then you can scale down the workload. For this, you can, I don't know, you can think of, we can think together. I don't know exactly what triggers for the pure watt token per watt economy could trigger that. And scalers, yeah, we can also look into it together. It's some topics that you can bring to the environmental sustainability group, because this is exactly what we're looking for, like people thinking about these problems and finding the right thing. Thank you.
Next, I have some question about Kepler. You said that for computing the power used for the bare metal service is easy, but what about the virtualization? Is say that you have to rely on machine learning, right?
Yeah.
So what metric do you use to train that model? Like how many? It depends a lot on what virtualization service do you use for, like VMware or OpenStack?
Yeah, so different, of course. This is what the model needs to know, right? Yes. So how to correlate the bare metal consumption with the virtual machine consumption.
Yes. So and what's an input? I want to know about that more.
Okay. No. I don't know right now, but I can look into it. All right. So you mean the input from the bare metal is the power consumption?
Yes.
That comes from IPMI, from different inputs in the kernel. Yeah. So you can tie in also different sensors as well. So you can actually have sensor feeding into the model, and I'm talking about like a power meters at the source, right? So and then you can measure it in the server. If there is a discrepancy, you can compensate for that, because it means that you are dissipating power between the PDU and the server itself. Right. So you need to know that to understand the real total efficiency of your server. Yes. And this is important. So
yes, thank you for your answer.
Thank you.